In this first lecture of special relativity, we revise the concept of equation of motion and frame of reference that were already introduced to you when studying mechanics. Given a frame of reference, that is, setting the space and time coordinate of our system, the equation of motion of a moving body is nothing but the position as a function of time. The body's velocity and acceleration can be computed by taking the first and second derivatives of the position with respect to the time. The first example of equation of motion that we consider is a body moving with constant velocity. We showed that its acceleration is indeed zero, and, by performing integration, we demonstrated that its equation of motion is a linear function of time. The second example was the one of a body moving under constraints of constant acceleration. By integrating once and twice with respect to time, we obtained the body's velocity and position respectively. We can observe that in this case the equation of motion is a quadratic function of time. The third and last example that we consider is a body moving at constant rotation. We discussed why the equation of motion results in the reported formulas and computed the body's velocity and acceleration. We proved that the acceleration is always opposite to the position, and, as by definition, that the velocity amplitude is indeed constant. We finally discussed how the equation of motion depends on the choice of frame of reference. Given two different frames, let's say frame number 1 and frame number 2, the spatial and time coordinates depend on the frame chosen, hence the equation of motion. However, the equation of motions can be mathematically related if one knows how to relate the two frames. We consider, for simplicity, the case where the two frames are spatially and time translated, and one does not move with respect to the other. One can express the spatial and time coordinates in the first frame as the spatial and time coordinates in the second frame, plus the spatial and time translations of the second frame with respect to the first. This operation can be performed as a matrix addition.